we can also have the presentation recorded for as this video and slides will be also shared in the Clean Bus Europe platform website as always. So we'll start the recording now. Okay. So good morning, everybody. Good morning, Francois. Good morning, everyone.
Good morning.
Welcome to this 11th webinar of the Clean Bus Europe platform today on battery focus, safety, second life recycling. Our speaker today is Professor Dr. Engineer Maitane Berecibar. Let me present her first. So she is a said doctor engineer. First, can everyone mute themselves? Please.
Monsieur François?
Yeah, that's it. Sorry for that, Maitane. So as we were saying, Maitane is an electrical and electronics engineer, doctorate in engineering of science at the VUB, Vrije Universiteit in Brussels in 2017. And she is leading and she is the head of the Battery Innovation Center in the MOBI Research Group at VUB since 2019. She is in charge of research and development, innovation and strategy in the field of batteries, and she was a great colleague and contributed to the Assured project in which we had the pleasure to work from UITP with her during the last 4 years. So thank you, Maitane, for that, and thank you for accepting this invitation to participate in this webinar. The program for today, I will be giving this short introduction and then we will move quickly to Maitane's presentation on battery technology, what's today available and what's coming in the future, what's the insights for battery health and safety, and maybe second life opportunities. After that, we will have a Q&A session, but during the presentation, if you have any question already, just please feel free to put it in the chat and we will go through it afterwards. Otherwise, after the presentation, we really invite you all to raise the hands, turn your camera on and put the question out loud to everyone. Just in terms of etiquette, please mute everyone your microphones. Turn your camera off while Maitane is presenting and just turn it on when you would like to present after raising your hand, or sorry, to ask a question after raising your hand. So without further ado, Maitane, the floor is yours.
Thank you very much, Manel. And meanwhile, I put in the slides, I want to thank all the UITP group and community for having me in this workshop focusing on batteries. So thanks a lot. And of course, it was a pleasure to work together with you in the short challenge that we had recently. And I hope that we will have more challenges soon together. So thank you very much. Thanks for the nice presentation of myself. My name is Maitane Berecibar, and today we are going to see a little bit of an overview of what's going on in batteries, which are how does it look, the batteries of the future. And it's important to start understanding the expected growth in global battery demand. And actually this we can see from this graph. We can see it in two different perspectives. On the left side, we can see the expected growth by application, and on the right side, we can see the expected growth in region. Comparing to 2018 to 2030, the growth is times 14 in both cases, by application and by region. And what we can see, of course, it's a huge part of the battery need will go to electric mobility in the application side. By region, China is leading. However, we are there in the European Union having as well a huge need on batteries. So, of course, we will need to be ready for that. We will need to have a lot of research activities on batteries, so to understand how to make them better. But first of all, what we need to understand is what is the menu, what are the different kind of batteries technologies that we can have already in place. So this we can see in an overview on this table. We start with a different type of chemistries of batteries, starting with lithium iron phosphate, nickel cobalt aluminum oxide, LMO, LCO, LTO, NMC, nickel manganese cobalt oxide technologies. Then we can have a little bit of comparison in performance, energy density, power density, calendar life, cycle life, safety and stability, and cost. And then we can see as well a bit of an overview of which could be the main applications in which these technologies can be used. Consumer electronics, power tools, light-duty vehicle, cars, trucks or commercial vehicles, buses, and grid we see as well. Of course, for this dedicated workshop, buses, it's on the spotlight for today. And as we can see, we can go here to the end of the table, where we can see that LTO technology, NMC technology are the battery technology that fits better in these different possibilities for buses technology. Why? Of course, because of, for example, the energy density that NMC offers, power capabilities that LTO offers, but they will come as well. Apart from this, let's say, state of the art, they will come as well, and we are working on different technologies to make them better. What we are working is on high energy NMC. Actually, depending on the one that we are focusing, it's already ready, or there are more activities on research to do on this technology. And I want to highlight as well solid state batteries, that we are going to talk a little bit more about this technology in the next slides. So let's go a little bit into the understanding of why solid state and what is going on in the recent years with this track on advantages and better battery technology. This graph, as we can see, it gives us a little bit of an understanding on facts, on numbers, depending on the volumetric energy density in watt hour per liter. In the horizontal axis, in the vertical axis, we have the gravimetric energy density in the unit of watt hour per kilogram. Here, the starting point, generation 1 on LFP, we see that it has the lower energy densities. However, when we jumped to NMC technology, which is generation 2 and 3, depending on the research that is ongoing there, we can see that there is already a substantial jump. However, within the NMC technology, we can see that there has been already a huge research actions to make the technology better in terms of these energy densities. So we started with the NMC 111, and we continued to, let's say, what we are working today with NMC 910. This is fantastic because of two main reasons. What we can see in the graph is that we are going to higher energy densities. That's very great. However, as well, it's very interesting to go into this trajectory because this technology is more sustainable. We are increasing the nickel content and we are decreasing the cobalt content, which is a critical material today. So we have already made a huge jump there in that technology. But we are expecting with more research activities on this technology, on NMC, to even go to higher volumetric energy densities in this case. But you can see here in green the box of the practical limits on this technology. It's very difficult that we will go farther than that. So as you can see in the next ball, or in the next generation 4, that is solid state technology, we are making again a huge jump on both energy densities, volumetric, gravimetric. But we can see as well that there are some practical limits. Within this solid state technology, there will be as well a different menu of higher and lower energy densities, depending on specifically which solid state technology we are working. However, I want to highlight as well this last one, lithium sulfur generation 5. Here, what we can see is that the volumetric energy density stays. However, the gravimetric energy density, it will be quite comparable to solid state. This is something very interesting. Why? Because we have a lot of sulfur, is abundant, so therefore the cost will be lower, and this technology will be, of course, more sustainable. But of course, as well, as we are seeing with the different colors and the different boxes, we have practical limits. But this technology is as well of great interest as of today. So we are seeing that there are different kind of technologies that we are now understanding, and there can be a bigger menu. We started with lead acid, nickel cadmium, nickel metal hydride technology, lithium ion. But as of today, the main objective is not only to focus on solid state with lithium metal, that obviously for mobility is the key technology that we are working on, and we are waiting to have excellent research, but we will need to as well diversify on different type of technologies, on different kind of materials, raw materials that we are using in these batteries. That's why there is a research ongoing on magnesium, zinc, calcium, a lot ongoing on sodium ion, and as I was explaining before as well, a lot on lithium sulfur technology. So what's going on with solid state? Solid state is promising, it's ongoing. However, we still need a little bit of time to have solid results that can go quickly to the market. So we at the department, we are working on this technology. We are developing functional coatings to be used in this. This is a little bit kind of pictures of what we are developing in the lab. So we are working with the PVDF-based solid polymer electrolytes so that they can be self-standing, and with ceramic fillers like LLZO to be added to the solid polymer electrolyte, and to at the end prepare this composite of solid polymer electrolyte. At the end, we need to test everything together so that we can create a battery. This is something that has been already ongoing in the lab, in the Battery Innovation Center, but today we are also focusing into higher objectives. We have an European project that has just recently started some months ago called MOBI-VUB, and here what we are working is on solid state technology, next generation technology, and the aim is to have an energy density of 400 watt-hour per kilogram. The key here, of course, is to develop the technology to increase the energy density, but as well, this will come not only on the compounds and the materials that we are going to use, but also on the manufacturing technique. This will really play a role in how we are going to move forward towards the feasibility of solid-state batteries. And in this project, we are going to use innovative manufacturing techniques counting with, for example, 3D printing techniques. So here we have a two vision understanding on this project. We are definitely going to work on the next coming mobility batteries, but we are also going to work on enhancing and making better the battery manufacturing process of batteries. And we will talk about this as well a bit later on in the slides. So I'm talking a lot about the technology, the materials, how to have higher energy densities. That would be the main point and the main need for mobility. But we are as well having a lot of research actions, as I was saying, with the NMC technology, for example, that we are continuing to enhance and make better that technology. But there are other things that we can already take into consideration, already have in place in order to improve these current technologies. And there are different aspects that we will discuss in the presentation. But first of all, we need to understand why is this. So we all know that degradation, battery degradation, is happening. How do we feel that? What is the effect that we see with battery degradation? So here we go to the right side of the slide. So what we can see is the capacity fade and the power fade of the batteries. This is the two effects that we can see that is happening on our batteries. Why is this happening? Which is the background degradation modes that we have? Well, there are different ones, depending if loss of lithium in battery is happening, depending on if loss of active anode material is happening, or depending on if loss of active cathode material is happening. You can see here that there are with different colors, and then if we go one step back, this is linked, and that's why the colors, to the different degradation mechanisms. This is what we can have a little bit of a summary of this, and what we can see is that, for example, binder decomposition can happen, graphite exfoliation can happen, structural disordering can happen, electrode particle cracking can happen, and this will lead to the different degradation modes. But of course, what we need to understand is why is this degradation mechanism happening? Because of different causes, because of current load, because of low temperature, because of mechanical stress on the battery. So these are the different causes that at the end creates those degradation mechanisms. We will need to use the batteries in the best way within some limitations, but of course we will need to try to make or stop these degradation mechanisms as much as possible, or try to reduce their magnitude, or try to make them slower that it will happen in time. So for this, there are possibilities. If we can see, for example, this is a little bit of another kind of overview of what can happen in the different parts of the battery, in the anodic side, in the cathodic side, or the different parts of the battery. So we can see that different degradation can happen in pulverization and electrical isolation, dendrites, solid electrolyte interface growth, transition metal dissolution, microcrackling, and electrolyte penetration. And actually, where you can see the rows, we are already working at the European level on how to stop and make them as low as possible these degradation mechanisms that can occur in a cell. And how can we do this? This is a little bit the key question. So here I have an example that I think it's very nice to understand what is self-healing, what is a self-healing functionality. What we can see in the image is the example of using silicon. We are using silicon more and more in for example, high energy NMC batteries, because with the use of silicon, we increase the energy density of the batteries. Therefore, it's very interesting. However, with silicon, we have a problem, because silicon, when we are through the cycles of charging, discharging, lithiating, delithiating, the silicon expands. That's what we see in the figure above. So when we expand after many times of charging, discharging, the silicon can go to a breaking point. And there, of course, we are losing the property that silicon is bringing to batteries. So with this self-healing idea, what we can is use a self-healing coating that will be applied on those layers, and then we can protect that material so that even though the battery will be continuing charging and discharging and expanding, it will create this protection layer. So in this consists self-healing. Here is an example with silicon. However, we were explaining that many different things can happen. So many different self-healing functionalities are now on the research area. And actually, this is something that we are doing today in a project that we are actually coordinating that is called VUB Forever. In this project, VUB Forever, we are not only focusing on the silicon self-healing functionality, that would be this first bullet point, that silicon particles coated with self-healing polymer binders, but we are also targeting other kind of self-healing functionalities that can be applied to the anodic side or to the cathodic side, with embedded into ionogels with the high capacity of anodes and the high energy cathode materials of core shell morphology. So different kind of possible self-healing functionalities. Okay, now we have seen a little bit what is this possible self-healing functionality, but there is something else that is occurring today in the research world on batteries, that is sensors. As we can see here, this will be a little bit of a future battery that is has a optical fiber inside the battery that could be connected wireless to a GPS satellite to provide information wherever is needed. This is a little bit the idea. Where is this coming from? From sensors inside the cells. Sensors can be applied inside the cell, that like we are seeing here in this figure, within the different battery layers, separator, cathode, anode, etc. But they could also be applied on top of the sensors, on top of the batteries, and that will be, I will explain it in the next slide. But as you can see, there are many different sensors that we can use in the battery field. So here there is a little bit of an understanding of some kind of sensors: electrochemical, electrical, acoustic. These are optical fibers, and this is as well coming from optical fiber spectroscopy. Why do we want to use these sensors in the cells? Because they can provide information about the status of the battery, the status of the material. So some of them can be linked to better state of charge algorithm development, state of health, understanding thermal, strain, pressure, crack, molecular understanding, safety, all these different characteristics that we can understand better from the battery. And as you can see, depending on the type of sensor, they can be a bit weaker in some of the characteristics or phenomena or parameters, or they can be better in green in some of the phenomena. So we have there a little bit of an understanding today of what can this sensor bring us. But as I was saying, some sensors can be inside the cell, embedded, and some other sensors can be on top of the cells. This is a project, Spartacus. It's a project in which we are working on. And in this case, for example, the sensors are printed in a circuit board. This is the picture of it, and they are on top of the cell. So in this project, we are understanding different kinds of sensors: mechanical, acoustic, temperature, electrochemical, chemical impedance spectroscopy sensors. And here what we are focusing, we at the Battery Innovation Center, is to develop novel state of charge, state of health, state of power, state of X algorithms to develop new novel battery management systems. Where can we use these batteries with sensors? Anywhere, and very likely for electromobility applications, of course, like passenger cars and buses, that will at the end have a better understanding of what's going on in the batteries. Yes, but what is going on today is that we are going to integrate both of them. I was talking about self-healing, I was talking about sensors, but both of them, they are going to be now integrated. So we are going to understand what the sensor is saying. So if a sensor creates a warning, well, this is going bad, let's say, then the self-healing functionality can maybe act through some triggering effects. This will lead to, at the end, synergies between sensors, self-healing, and novel understanding of battery management systems. I cannot say more than that. Things are ongoing, but soon we will have coming work to work specifically on this, which is extremely interesting. Additionally to this, when we are talking about cell level, there is something extremely important that I was saying as well before with solid state batteries. Manufacturing, how we are manufacturing the battery cells. We are understanding that the process needs to be in research state, because of course we have many different steps, as you can see here in the slide. We start with mixing, coating, calendaring, cutting, stacking, filling, formation, and then we have the cells. So here what we can see is that by creating a digital manufacturing framework, we will definitely increase the battery quality. In here, there is something as well that will come from our side. It will be coming soon. We will have new coming research activities that will really play a role in how we are going to have these first life new batteries, and how at the end they are going to perform together in a battery pack. So we will have longer lifetime battery packs. So yes, coming soon, new activities on here. I hope I will let you know some of this soon. So these were a little bit all the activities that they are ongoing right now at the cell level. But of course, there are other activities that we can do at module and pack level at research activities. We can start with the understanding of thermal management. Thermal management, we have already had, we have an understanding of different possibilities on air-based thermal management, liquid-based thermal management, hybrid. But of course, when we are going to challenges like fast charging, then we will need to really have an understanding of how to really enhance and optimize the battery thermal management and the system itself. So in this project, the Selfie project that we are now actually finalizing, in the finalizing stage, the objective was to how to make it possible, fast charging up to 5C by enhancing the thermal management system and by creating a smart modular battery pack. In this case, the use case is Fiat Tableau, and now we are in the implementation and validation stage. For this modular battery pack, we were using a refrigerant cooling system and phase change material for this thermal storage system. And at the end, what we are aiming is to keep the battery temperature within, of course, the optimal window to prevent the possible overheating that can be created due to fast charging. And here we have some results. We have developed these results in the Battery Innovation Center. We have had an evolution of the working. So because we have started at, for example, cell level. At battery cell level, we had a different experimental research ongoing, and we have developed different thermal management performance assessment based on those results. But of course, we did not keep our results at cell level, but we also went to the module level. This is the figure that you can see, the module that we developed at the Battery Innovation Center of prismatic cells. And here we have different validation, and we had an assessment of different possible solutions to be used as thermal management. And actually, this graph here gives a little bit the overview of different thermal management systems that can be used. So as we can see, the temperature reduction is the biggest and the one that keeps the battery in the more comfortable for the battery, and the most successful battery thermal management in this case for an passenger car was the use of PCM, phase change material, together with liquid cooling refrigerant thermal management. Good. There are other activities, other actions that can be done at module level. And for example, this can be real-time cloud simulations. Here there is another project in which has been closed not so long ago, which is called Panda. And the objective of this project is to reduce the time to market. The objective here specifically was to reduce it by 20% through standardization of models and simulations. So here we could use models and reuse them for different kind of tasks, and we could as well reduce the real testing through using virtual testing platforms. In this case, we had a use case of a full electric Renault Zoe that we have tested with these real-time cloud simulations. Here as well, a little bit in detail, what we did. We have a different level strategy, as you can see. Here in the first level, higher level, we have the cloud, where we have uploaded all the different models, and then these models are linked to the different interfaces. And in this, we have real-time simulators in which we have used, in this case, iPhone hardware in the loop. We had two of them in which, because we were going to test two different use cases. In this case, we have the hardware in the loop testing for the battery itself that we did, and we tested at VUB in the Battery Innovation Center. And then we had as well the testing of the e-drive that was done through some partners within the project. So here we had the test of a standalone test for the EV components with the cloud models interconnected, and co-simulations in real time was happening as well between both of the tests that we were doing. So that was quite interesting to see within this project. But there is something else that we can do in this regard. And this is something that I want to as well comment from the Evolver project, in which the focus was to develop smart charging. The starting point from Sevolver was thinking a little bit of how we use the batteries today in an application. Are big batteries crucial for long distance trips? No? Do we need that specifically, or should we use a smaller battery in a more efficient way if we understand better the status and the performance of the battery? And actually, it's beneficial to use smaller batteries for climate change. So the objective of this project, it was to, again, use computational capabilities and big data, but to optimize the electric vehicle energy and thermal management. And in here, at the end, what we were understanding very well, and the objectives were to understand reliable range prediction, eco-routing, eco-driving, smart fast charging as well, and assured charging. In this project that it has been also finalized quite recently, we have developed an app in the Battery Innovation Center in which we could virtually simulate different frameworks, different simulations for the advanced energy and thermal management strategies, depending on how the battery is and depending on how the environmental temperature is, we could use the charging in one way or another. So this makes the charging protocol smarter. So then in this case, we could compensate performance differences from the batteries that were already tackled, and we could as well take into in consideration the environmental conditions, as I was saying. Good. We continue with other activities that they can be enhanced and sell at module and pack level. Here we are already understanding a lot on modeling. We have done a huge way on modeling, data-driven, physics-based, equivalent circuit models, empirical models, and so on. But now what we are going through is towards a battery digital twin. So to understand from all these models that they have been developed, how to link them between them and how to use the one that fits better depending on the technology. And here, many things as well will come soon in order to enhance the usage of the battery at module and pack level as well. There is another topic that I would like to discuss with all of you, that is Second Life. Second Life, I call this dream or reality. Well, so in Second Life, there is already a lot ongoing for different scenarios. But where do we consider Second Life? Until now, we understand that the first usage comes from 100% to 80% capacity, and second usage should be between 80 and around 60%. After that, it should be recycled. This is what we have been understanding. However, I would like to say that through the enhancement of the technology by using other kind of materials, sensors, self-healing properties, better thermal management, and digital twins, for example, we will be able to use more cycles until we end up in this second usage, for example. But there are possibilities. There are projects that now, for example, we are working on, we are targeting. First, there is a project that is called Clever, just started some months, in which we are developing batteries and algorithms to be used in buildings. So this is the concept of this project, is to use a second type battery to be used in industrial or commercial buildings. For this, what we can be take the advantage of these batteries is that they can be used, for example, for peak shaving activities, or they could be also be used for understanding a smart electric vehicle charging, where we can have a smart algorithm, and this will be scheduled in different ways to provide the needed energy to the electric vehicles when needed and use that energy when needed. This is already ongoing. Another use case is grid applications. Here we have another just started project that is called Reassure. And here we are going to develop a multi-approach technique or platform to integrate and use smartly the different assets of a specific grid application. It is very important, and it's what is going to happen within the project, is to understand the different context. Which kind of operating assets are we having? Do we have PV? Do we have battery? Do we have wind miles? Do we have HVAC, etc.? And as well, the different operating conditions at different moments. So here, the objective is to facilitate the integration of the databases that we have with real world and link them to different sources, different models that are already happening. So that's why it is important to investigate the existing techniques that we have to use efficiently the different assets or energy vectors. And here as well, standardization is key so that we can go from lab to demo testing. And this is now starting in this case, in this project. I would like to emphasize as well vehicle to grid. These are some results that we did in the Battery Innovation Center, concretely in my group, in which we were testing two different scenarios. And I think it's very important and very, very nice to highlight these results. We were comparing two scenarios in which we were using our electric vehicle to go home, to come back from work, and to charge it, or to use the electric vehicle to go to work, to come back home, and then use it for a residential usage. And our idea here, our research question was how this really impacts the battery aging, the battery degradation. Is this a drastic comparison, or is this a drastic degradation that we are having when using vehicle to grid and when not using vehicle to grid? And what we saw preliminary in our tests that we developed in the lab is that we did not see immediate extra negative effect that could happen in the aging of a battery comparing to a usage without V2G. And I think it's really fantastic to show these results. We are continuing testing. This was, of course, an early research that we did, but we are continuing testing with lower capacities on the batteries. So what we are discussing about possibilities for second life when using them in a residential case, when using them in a grid application, and even also for possibility of vehicle to grid, although we consider this first life, it is important and key to develop state of health and remaining useful life estimation algorithms. We have developed this very much for first life. So there we have a lot of background understanding on how to do this, but we will need to go a little bit a deep step forwards. Here we are now understanding not only physics-based models, but also hybrid-based models. And what we need to understand as well is which degradation is happening in the cells, so that we will understand better how the technology and the performance will evolve. Because depending on the degradation that is happening, will evolve more drastically or more smoothly. So a combination of both the modelings of physics-based and hybrid-based together with the degradation is key, not only in first life, but also in second life. And that will, at the end, enable the possibilities to use efficiently and smartly in a realistic scenario a second life battery, and will as well enable the possibility of understanding when to start recycling, because we have an understanding, okay, we should not go lower than 60%, but still we need to go into research that and see if that's a realistic percentage, or should we go, for example, in a lower capacity percentage. Good. So this was a little bit the activities that we do, and of course, this is what we do in the battery team, in the Battery Innovation Center, with some needed lab facilities. So we see our activities in batteries at different stages within the circular understanding on batteries. As I said, we work on next generation battery technologies with different kind of novel technologies like solid state, silicon-based technologies, self-healing in something extremely important that we are tackling in the team, manufacturing as well, how to upscale, how to optimize this fabrication process, and how to include these sensors, embedded sensors on top of the cells, how to use them efficiently. Where we have been discussing as well is on the usage, focusing in this workshop on mobility modeling is needed, electrochemical, thermal, electrical lifetime, and smart state of X estimation, state of health. It's needed as well, and it's becoming also on the research topics always under research together with the thermal management and cooling systems. We are now in this research of using phase-change materials that they give very good results. We are part of a standardization committees. We are part of the TC69 and TC21. So we understand very well which kind of standards are applied, and a little bit as well on the battery directive that is coming in place. We are a deep understanding on what's going on there. But if we go to second life and recyclability, of course, there are other things that we take into consideration. We understand we can go to post-mortem, we can adapt the different models that we were using in first life, and we have developed a tool actually for second life to understand this battery. What should we do? Should we use it in another application? In which application precisely? Or should we recycle it? I am chairing the safety task at Batteries Europe. And then, of course, closing this loop, we have raw materials, understanding social aspects, LCA, eco-design, and cost evaluation. That's also something very interesting for batteries. So for all these activities, we need a lot of infrastructure. We need a big lab. We have 300 channels to test batteries. We have 12 climate chambers like the one you see here in the slides. Actually, 3 of them are walking chambers, so that you yourself, you can go, so that we can have the place to test a bigger module, a battery pack. We have impedance spectroscopy channels for the thermal activities. We have an imaging equipment and a management platform. And we have as well a DS space to translate all these algorithms to a microcontroller. But when we are talking about solid state, manufacturing, sensors, then we have other kind of equipment. We have an argon glove box, the one you see in the figure. We have in situ XRD. This is fantastic. It's quite unique that we have this technology, and we have a new open dry room. This dry room looks like this. There is a lot of equipment that we have to manufacture the next coming technologies that we can develop pouch cells in our lab. Conclusions, yes. Quickly here, we are working on high energy densities. We are working on smart functionalities with sensors, with self-healing. We are working on battery manufacturing processes. This is extremely important at the end to have a longer lifetime battery pack. Fast charging is becoming more feasible through the adequate thermal management strategies. Real-time cloud simulations are now in place to reduce the time to market and to use a smart charging technology that could be used for efficient sizing and usage of the battery. And Second Life right now is under research for demos in buildings and in grid applications. And for this, it's very critical and key to understand the state of health and remaining useful life of the batteries, to use those batteries in the best and safe performance. That was everything from my side. I hope that you like the workshop. Thanks a lot, and open for questions, of course.
Thank you, Maitane. Thank you very much for your presentation. I'm sure all the participants will join me in thanking you for this didactic presentation on such a interesting but also complicated topic for people who is not an expert as myself, I must admit. So thank you very much for allowing us to grasp a bit more on this. So yeah, I think we have around 10 minutes to allow presentation questions. So we have some of them already in the chat, but maybe Alejandro, you would like to raise your questions as it was first by presenting yourself and raising and turning on your camera. Would that be okay for you?
Yes. Hi. Thank you for the last presentation. I just posted a couple of questions. The first is 3 questions. The first 2 concern NMC. In your slide on specific energy and energy density, you show that the more cobalt we have in NMC, the less energy dense the batteries are, the less specific energy they have. Can you confirm this? I was of the idea that the more cobalt you had, the more energy dense the batteries would be.
Yes. So the need here is to increase the nickel on NMC. Then we will have a high energy density. But it normally, when we are talking about high energy NMC, is because we are in one hand increasing the nickel, but we are as well using silicon on the anodic side together with graphite, and that both together increases the energy density. However, cobalt, the main concern is to use it as less as possible. So because of sustainability concerns and because it's very critical, cobalt. So that's the main idea with cobalt. We are trying to reduce it, but still increase the energy density with other materials.
Right. What if you take silicon out of the equation? Just graphite on the one side, on the other side, you just go down with the cobalt. Do you really have a less higher energy density with less cobalt?
Well, you need to have a little bit of a balance. It's a bit what I was showing as well in the graphite with the practical limits. We went from 111 to 910. So then at the end we need to go to a different balances, and then cobalt is there always. Is needed, even though it's in a very minimal content. But there was there a track that we were having, like for example 6 to 2, 6 nickel, 2 manganese, 2 cobalt, and then 8-1-1, for example 8 nickel, 1 manganese, 1 cobalt, and in that's a little bit the trend. So cobalt has been there without keeping the silicon outside, but yes, it's increasing the energy density. Yes.
Thanks. I'm gonna jump right through to the third question. LFP, it is considered as being safer than most of other battery chemistries. Is this true, considering that safety depends on many other factors?
Yes.
Aside from the mere choice of your chemicals or materials, depends also on porosity and thickness of the electrode. And at the end of the day, also on the battery pack level and the battery management system. What are your thoughts on that statement? LFP being safer.
Yes, it's a very interesting question, this one. It is always considered LFP safer technology. However, of course, depending on how you look at it. If you compare the thermal runaway starting point on temperature, it's true that in LFP, the starting point on the temperature, it will be at higher temperature if we compare it, for example, with an NMC technology. However, safety, it's also other kind of things, other kind of safety issues can happen. So then in that sense, we may not have such a bigger difference. So depending a little bit on what it is the focus. But of course, it's true that thermal runaway is one of the biggest issues that can happen. And that's why we consider this.
Thank you.
Thanks you. Thanks to you to the questions.
Thank you. The next one is from Adnan.
Yes.
Yes.
Thank you. And thank you also for this presentation. I have two questions. The first one is regarding the modeling that you are doing within the laboratory. Do you have how do you scale up the model from the cell level to the pack? Do you have also some experimentation on the pack level, or you just work with the cell level and then tune in the model to have a pack and the final model?
So in our lab, we can test both cell and modules. So at the end, as we have seen in some of the slides, we have 300 channels to test the battery. So this means that we are testing the batteries at controlled temperature, controlled humidity at different C rates, different temperatures, different DODs, calendar life also. Obviously, we test. From those data, we developed different kind of models. Now, smart models by using machine learning techniques, and then what we can do is validate this at cell level, but we can actually do the same action at module level as well. We can test the modules, developed the different models, and validate the different models. And this we can do on lifetime perspective, but also on thermal management. For example, as I was saying, we can develop the different cooling strategies and cooling system, and test it with the different application, for example.
Okay, thank you. And do you see some big difference between the cell model compared to the module, I would say, model with a different distribution of the temperature? And do you see some, big differences on the lifetime, for example, or other things?
It's not straightforward. There is a big jump, as you are saying, from the cell to the module level. So that's why we, from our equipment capabilities, we always like to have the full scope, because it's really critical to understand that jump, to understand from cell to what happens in the module. What we can understand, of course, is that a cell in a module level that is on one side, if we are talking about thermal, if it is in one side or if it is in the middle of the module, it has a different impact. So that's how we fulfill the scope.
Okay, and just last question, does some standards or regulation exist on the usage of battery during the second life?
I know that something is right now ongoing. However, I'm not sure if there is something published yet, like that standard or regulation that it's in place. I would say no, that there is nothing today that we should comply for, I would say.
Okay, thank you.
Thanks.
Thank you. And we have another question on the chat from Benjamin Rollins. So yeah, it's related to how about the raw materials availability with such a high growth in the demand. Any insights, Maitane, for this?
Yes, well, that is a little bit what I wanted to clarify as well with one of the slides. We need to diversify. We need to diversify. We cannot only use the same technology for all applications. Definitely, there is a logic understanding that for mobility, solid state will be the main driven technology, but we need to start diversifying depending on which kind of mobility application. If it is for a small, let's say, golf cart, maybe there is a different need, so we can diversify and we can use other kind of more sustainable technologies that they are as well now under research, and they are more sustainable.
Yeah, it is amazing, and it's been fantastic to learn how the scientific domain is helping the sector, improving and making sure that the clean vehicle and the zero emission development, vehicle development is actually more and more feasible, I would say. And we see more and more operators and authorities committed to this deployment of battery electric vehicles. So thank you, Maitane, for this. I think it's 2 minutes past 12. So if there is no more urgent questions, I think we can wrap up here. As always, the presentation will be available in our website of the Clean Bus Europe platform, and the recording as well. So without further ado, I wish you a very nice afternoon and end of the week from the Clean Bus Europe platform team. Goodbye and see you next time. Thank you, Maitane.
Thank you very much. Bye-bye.
Thank you very much. Thank you. Very inspiring. Thank you.
See you in a while,
bye-bye.
Françoise, in Paris.
Thank you very much.
Thank you all.
Bye.